Hello everyone, welcome to another class on the course of Quantum Theory of Many-Body Systems in Condensed Matter. My name is Luis Gregorio Dias and I'm a professor here at the Institute of Physics at the University of São Paulo. So in today's class we're going to go over Dyson's equations and the self-energy. And we're going to start with Dyson's equations for single particle Green's functions we saw in a previous class on Green's functions. Then we're going to go over how we can generalize this equation for time-ordered Green's functions and define the self-energy, both the improper and the proper self-energies, and see how Dyson's equations works in the momentum space. And probably we're going to end with a couple of examples. So let's go right into it. Alright, so let's start by reviewing the single particle Green's functions. Remember that if we have Schrodinger's equations with a given Hamiltonian, solution for a given energy will be given by this. So this would be a solution to this operator. And we also have the non-interacting Hamiltonian, say that this is sometimes we call the free Hamiltonian. So that H is H naught plus a perturbation. Okay, so that's the idea here. And this will have a solution that in principle is known. Okay, so we can, from this operator, we can define the single particle Green's functions, which is a solution of applying this operator to this function and obtaining the delta function r minus r prime. Same thing for the free Hamiltonian. You get something that is essentially given. In principle, you can calculate this, which we're calling G naught, the non-interacting Green's functions. So in a sense, this is, you can see that, this will be a 2-point Green's functions, r prime to r, at a given energy E, right? So this is not a time-dependent Green's functions. It's given for a fixed energy. All right, but it essentially will illustrate what we want, and perhaps we'll make the connection with the time-ordered Green's functions that we're going to see later. All right, so the point here is that if I know these Green's functions, I can obtain the solutions for the Schrodinger's equations for a given energy E. How we solve these integral equations, sometimes called the Lippmann-Schwinger equations, where the Green's functions is essentially the kernel, and this is the potential. Remember, H is H naught plus this potential. Okay, so this is the free Hamiltonian. And so if I know G naught and I know the free solution, I can in principle obtain the solutions for the interacting case by solving these integral equations. Notice that Phe appears both here and here, so I could in principle get a solution in series. All right. Formally, I can also write the Lippmann-Schwinger equation in terms of the interacting Green's functions, and what appears here is just phi naught, the free solution. But this is not too useful, since it will be useful if I want to write G in series of G naught. But in general, if I want to get the solution, then this one is more useful in a sense. Now, as I said, if I combine these two, I can get an integral solution for the interacting Green's functions in terms of the non-interacting one, and that's sometimes called Dyson's equations. So here I'm essentially writing an integral equation for G in terms of G naught. It's very similar to this one in a sense, okay? So where you have the zero order approximation for the Green's functions is precisely the non-interacting Green's functions, but then you have this integral equation that involves the non-interacting and the interacting. Here is single particle, right? So I'm saying interacting, but what I really mean is in the presence of these one-body potential, okay? So this is H naught plus this one-body potential. But this is Dyson's equation, okay? So in a sense is the Green's functions for H, which is H naught plus V, in terms of the Green's functions for H naught. Now, let's take a look and see how we can pictorially see what's going on here in terms of diagrams, quote unquote. So if we write these Green's functions, I can essentially substitute here in this integral different approximations for g. So for instance, if I replace the first term here would be by replacing g by g naught, right, which is the zero order approximation, and that will give me the first order term. So if I write these equations pictorially like this, g equals g naught plus g naught v g, remember that here there's an implied integral over r1, since here the propagation goes from r prime to r1, potential at r1, and then free propagation from r1 to r. Okay, so if I have a term like this, that will involve two integrals, right? So I'll have an r1 here and an r2 here, right? So, but if I have this structure, I can iteratively replace g by in different orders of the potential v here. So the first order would be g naught, second order would be g naught v g naught. Then I take this term and substitute here. I'll have g naught v g naught v g naught, and so on and so forth. And then we can write this as a series of diagrams if you want, right? So here, yeah, this should be r prime down here. Well, it depends on where you're propagating to. So this is kind of, we're propagating this way down. So the first term would be the free, which is this thin line, and g is the thick line. First order term would be, r1 to r prime to r1, and then from r1 to r, one interaction. Then the second order term would be r1, r prime to r1, r1 to r2, r2 to r, and so on and so forth. So this is the idea of expressing the solution of Dyson's equations in terms of these diagrams. And you can even write the equation itself in terms of these diagrams. I would essentially take something like this. I would take the thick line from r1 from r prime to r1 here, and then a thin line from r1 to r. So if I replace this segment by a thick line segment and forget, and essentially that will give me already the equation, right? So there would be a thick line here that would represent g from r1 to r prime to r, and illustrates how we can then represent this series in V in terms of this perturbative series, if you wish, in terms of these diagrams. Now let's go into the blackboard and see how we can look at this pictorial view and see how we can apply that not to single particle Green's functions like this ones, but to the many-body time-ordered Green's functions that we saw in the previous class. The previous class, then, we discussed how we can expand the time-ordered Green's functions in terms of Feynman diagrams. And here I'm already putting the Green's functions in momentum and frequency domain. We saw that in the previous class as well. And these are the diagrams for zero, which is simply the non-interacting propagator, the G with an index 0 here. First order in interaction, so we have only one interacting line, okay? And these are the diagrams for second order, meaning 2 interacting lines and 5 propagating lines, right? So the yellow lines corresponds to free propagators like this. Now, these diagrams for n equals 2 you notice that there are two types of them. These four here are essentially the diagram, two diagrams of the previous order. In this case, these two diagrams for the first order, connected to each other by a free propagating line. All right. So it's like here I have, you know, this diagram, and I connect it to put another line here and another propagator, and I obtain this one. They should be in the expansion, since they're all second order contributions, second order terms. But they differ from these others by one fact, that since they're essentially two first order diagrams connected by a propagating line, it means that at some point I can kind of cut one propagating line and divide these diagrams into two first order diagrams. So that's what they call reducible. You can cut, like here, let's give an example. Say here, if I come with a scissor and cut it here, that will essentially become two first order diagrams. Same thing here, same thing here, same thing here. So these are all reducible diagrams. Now these other 6 diagrams, they're not reducible, meaning that there's no way I can cut them and cut a single propagating line, a single free propagating line, a yellow line here, and reduce them to two separate diagrams, first order diagrams. You may say, okay, this looks like a first order diagram. Yeah, but you know, like they are similar to these, but I cannot cut it here, for instance, without cutting a interacting line. So this cannot be done. And so these are sometimes called the irreducible diagrams, and that's going to be important for us. For second order, these are the 6 irreducible Feynman diagrams with 2 interacting lines and 5 propagating lines. Notice again, in all these I have 5 propagating lines. You can count, for instance, here I have 1, 2, 3, 4, 5. Same thing here, I have this propagating line from here to here, 1, another here, 2, another here, 3, another here, 4, and I have this loop. So I can count in all of them I have 5 propagating lines and 2 interacting lines, and as it should for second order diagrams. Okay, so the question is, can we rewrite this sum as a Dyson's equation? That's where we're gonna get at. All right, so let's take a look at this reducible diagrams. Let's take this one as an example and see why is this reducible? What's going on here, and how can we look only at the irreducible diagrams to form this one? Well, as I said, this diagram you can think as a product of 3 diagrams, right? One, if I know cutting right here, I said this by definition this is a reducible diagram because it can cut a free propagating line. So that means that somehow I can separate this in 3, like this one, and notice that I'm putting the momentum here, right? So this is K, there's a momentum Q here for the interacting line, then this line has K minus Q, etc. So this is a propagating line, a free propagating line with momentum K, the same K and that is entering here, which essentially gives the K for the interacting Green's functions. Okay, so I can separate this into 3. This diagram, right, with two propagating lines and a single interacting line, and ends here, times this free propagating line times this other diagram, which is essentially identical to this, except for, you know, it's reverted. But that means that if I strip down these legs, you know, this is essentially a combination of free propagating lines with the momentum k, and this diagram here, which is has a line. So this is a irreducible diagram, interacting irreducible, which is one leg, one pre-propagating with momentum k minus q, and an interacting line with momentum q. So if I take this core diagram, right, and add a line here and a line there and combine these, I can build these reducible diagrams. So that tells us that if I take a series of diagrams like that, right, where I start not in a leg, but I start at this point and involve only the interactions, that will tell me something about the contribution from the interactions to this diagram. And if you take a series of diagrams like that, we form what we call the proper self-energy, which is just a sum of irreducible diagrams just like this one. So the proper self-energy is defined here. I define with a minus I times this symbol with a star. Typically, different authors prefer different notations here, but I'm taking it this with a star. And I'm representing by this ball in magenta here with these 2 points, right? So these 2 points are essentially refer to the point where the interacting line starts. One of the interacting line, the outer interacting line, starts and ends, okay? The top one. Here's the start and end at the same point, okay? Here in this diagram, these 2 points are these, right? And then you can have higher order diagrams. So in common, all these diagrams tell me that you cannot separate them in 2 other diagrams by cutting a single free propagating line, right? So I can then sum these and define what I'm calling the proper self-energy, right? So it's a sum of these irreducible diagrams. So pictorially, if I define my proper self-energy this way, I can go back and look at my interacting Green's functions. And here I'm representing, yeah, this is not too good. Here I'm representing this as this sum, okay? So yeah, this is just a line, sorry. Let me put it this way. This is just the free propagating line with a momentum k, okay? So this is it. This is the free propagating. So pictorially, what do we have? So I can draw my self-energy as this, as one leg with the momentum k entering the self-energy, and one leg with a momentum k exiting the self-energy. So what are these terms? Notice that here I essentially reordered all my sums and saying what's contained here are all the irreducible diagrams. So for instance, this term is in there, so I have this, I have that, so I have two legs, one here with a momentum entering, and one here with momentum exiting, and there is this term. This term is also there. Other irreducible diagrams in second order are there too. So one entering with momentum k, one exiting with momentum k, and so on and so forth. All these are there. Now, what's not in that first term, in this one, so all the reducible diagrams with one leg in and one leg out are contained here. Now, these diagrams are not there, but these diagrams are in the next term, which is this. So I have one leg coming in, one leg coming out, momentum k, right? The same momentum k as this. This is important. Okay. And another final. So I have now three legs entering a self-energy, and then the proper self-energy, exiting the proper self-energy, entering another self-energy, and so on. So remember, these balls are sums of diagrams, okay? So this will account for all diagrams which are reducible to two irreducible diagrams. So all these four will be included here. It's like, you know, I go in and I pick one of these two, but plug in here, propagate, pick another one of these two, propagate again. So how many do I have? Well, I have this one twice, this one twice, and two permutation of one of each of these, which is precisely the four diagrams that I have there. That's the first order, and I can keep going, right? And connecting two diagrams, say a second order reducible diagram here, and a first order there, I'll get a third order diagram, and so on and so forth. And I can keep doing this game and get, say, a diagram like this, right? Where I have now four legs, and I have, say, K, 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 okay? So, yeah, I can cut on any of these lines and get, you know, other diagrams that appear already in order, in previous orders. So these are all connections. So the first diagram here would be a third order diagram. So if I take three of these, or three of these, I'll get the first diagram here. So essentially I rearranged the series to look like this, okay? And now this already looks like a Dyson's equations, and we'll see how we can do. Notice that there's something repeating here, right? So I always have say an inline, and then I have this, and then I have this, 3, I have 1, 2, 3. So it looks like I'm getting, or if you want, you can say one line, one self-energy, and then if you look from here above, okay, what I get. So just above the first proper self-energy, what I have K, I have K ball K, K ball K, which is precisely this series, right? And that already tells us where our Dyson's equation is, right? So what I'm saying is that this, if I would do this and keep going, right? So this is precisely ij, the full interacting omega. Okay, so this series is essentially equal to this series, and there's where we get our Dyson's equations. So if this is true, let's draw it graphically, and you see what I mean. Let's go one step ahead. There. So this is now Dyson's equations. So I'm relating the interacting Green's function with a non-interacting one, right? So it's a non-interacting one, is the zero order term, plus what? Plus what I just mentioned. We have now a propagator, here free propagator with momentum k, frequency omega, coupled to the self-energy, the proper self-energy right here. And what's above here is a sum, which is essentially the same interacting Green's functions at the same k and same momentum. All right, so k omega, and this is also, so this is ig, this is the proper self-energy minus I sigma star, and this one is the free propagator ig naught. Okay, notice that I wrote this in k and omega space. I already done the Fourier transform, so these are essentially products of these functions. If I had done this in position space, and I could have done that, right? So there will be a propagation from say a position, say something like that. Oops. A position r prime at a time t prime to a position r at time t. So there will be 2 points here. This would be equal to a free propagator from r prime t prime to rt. But this would be a similar diagram, except that now I would have to have an integral, right? So over internal coordinates, it would be r prime t prime. Then the self-energy here would have a coordinate r1 t1, and then I would have the position here from say r2 t2 down to r, to r at time t. That would be in real space. But then I would have to write this as an integral equation, where this would be a 2-point function depend on r1 t1 and r2 t2, and I have to integrate it over r1 and r2 and t1 and t2. Okay, notice that these might have these are the 2 points. So this is the structure, right? And the idea is we can solve this, or we can express this in orders of the interaction by just solving the self energy, the proper self energy in different orders of the interaction potential here. And in principle, if I know the free propagators, I can simply express, at least in a given order, what is the Green's functions here. Okay, and they're gonna do an example later in this class. And as I mentioned in a slide where we introduced the single particle Green's functions and the Dyson's equations for it, we also show that in a similar form as that, there's another way to express a Dyson's equations here, where in the left or in the right hand side I only have free propagators, and I have the interacting Green's functions on the left hand side only. But here the kernel is not, so let me remove that, sorry, is not the proper self-energy with the one with only this disconnected diagrams, but the improper self-energy. So how does that Dyson's equations look? So if I try to express this then as the interacting propagator Ig times the free propagator Ig naught, and now two free propagators, one Ig naught here and one Ig naught there. This has to include all diagrams, all interaction diagrams, both the irreducible, like these ones, but also the reducible ones too. So that then with that I recover my original series. Let's take a look there, the one that I wrote in the very first slide. Then this is clear. I only take the legs out, the two legs out, the legs in and out, and all I'm left is with all the possible diagrams, both reducible and irreducible. But then there will be a self-energy there, right? If I just strip off the legs, the outer legs, this self-energy there is going to be called the improper self-energy, and that will involve all diagrams. So then there will be many more diagrams included here than in a proper self-energy, where I include only the irreducible diagrams. Okay. So, but again, this might not be too useful because I have to include all these reducible diagrams here, but it's another form for Dyson's equations. Okay, I'm gonna finish this class with an example where we're going to calculate the diagrams for the electron gas for the first order contribution. And this will illustrate how we can then use these tools to express, say, the first terms in the proper self-energy. It will be very similar. We're going to have two propagators here in front, and whatever is left is going to be the contribution from the proper self-energy. So we have these two diagrams, and they are reducible diagrams, right? You cannot cut them and separate them in two. So these would be the first diagrams in the proper self-energy. All right. So yeah, let me just put it here. Okay. So we're calculating the n=1 terms in the Green's functions. So we have here, say, the contribution from this diagram, right? And this other one. They're the two unconnected diagrams that will contribute to the first order term. So sometimes this diagram is called Hartree, and we're going to see the idea and why this is, and why it doesn't depend on the momentum of the frequency. So it's just a zero momentum contribution from the interaction, while this is the exchange or Fock, and we'll actually have a momentum here. So let's start by assigning the labels here as the Feynman diagram rules tells us to do. All right, so let's assign the momentum here. So let's take the Hartree diagram first. So we start with momentum k and frequency omega here, right, in the first leg. And we assign that. And in the last leg as well. Same here. Same here. And now we conserve momentum at each vertex and energy in each vertex as well. So you can even assign some dummy variable here and here, and then you figure out which one is which by doing the conservation of momentum. But in this case, this is clear, right? If in this vertex I have k coming in, I have k coming out, so the momentum here of this line has to be 0, right? So this is 0 momentum. And this is also 0 frequency. So remember, this comes from a line that propagates in same time. So these 2 points are at the same time. So we have to remember to include that exponential of I omega eta when we're considering here, right? But this is essentially 0 momentum and zero energy. Okay. Now, if this is 0, and let's call this Q, right? Or K prime. Let's call it this K prime. This is K prime entering here. That'll exit here. So this will be still the same K prime, it's just an internal variable. Also, this loop is a path that, if we go back to time domain, would start and end at the same time. All right, so this has frequency omega prime. It's going to be an internal variable. Well, here I have, if I have, say, K prime and omega prime here, and then I'll have for Q and omega Q. What do we have? Well, by conservation of momentum, then I have K prime coming, and I'll assign this in this direction, right? This Q in this direction. So it's entering this vertex and leaving this other one, right? I could assign it the other way around, just change the sign. So that means that I have K entering equals K prime plus Q. That means that K prime is actually K minus Q, and I have only one dummy variable left, which is Q. All right, so let's call this K minus Q, that's momentum, and the frequency, I'll have, whatever frequency I had here was omega prime. Then I'll have omega equals omega prime, but plus omega Q. Then as omega prime is just omega minus omega Q. Okay, so that's the momentum and frequencies associated with this propagating line. While in the interacting line, this is the momentum and the frequency, and of course has to finish with K omega. All right, so let's now write the expression for this diagram. For instance, let's start with the Hartree one. So here we go. So let's now write all the propagators. So I have here a propagator with K omega, another one with K omega. So I have IG naught, the free propagator at K omega squared. And I'm already included the spin indices here. So, just to provide the starting and end point here, sigma and sigma prime. here it could be, the diagonal. It's just that we're going to, that there will be a delta function here anyway. So this is I g naught k omega squared. Then there's the interaction line minus I times V, and the momentum is 0. Okay. So, and there's another propagator here at k prime omega prime, and k prime and omega prime are both in the internal variables or internal indices, and you have to integrate or sum over them. So there will be an integral in k prime and an integral in omega prime here. So this will factor out. I will be left with an integral in k prime and omega prime. Two other points, we have to add a -1 because of this fermionic loop here. There's this -1 here coming from the loop. And since this is propagation, an interacting line propagating in the same time, and here too, right? This is an important point. We have to add this e omega prime eta 1, right? Just to since this is an equal time propagation, especially here. This is an equal time propagation. Okay, so e omega prime eta 1. All right, so all we have to do now is to solve for this integral. So first thing we do is to figure out what's the overall sign of this term. So I have this -1 here, and I have this I squared, which is a -1 too, so you get a +1. Then I have this -I times I, so overall I get a +1 sign here. I have this g naught squared, k omega prime, and I have this v, which is 0 momentum. This is going to be important since we figure out that this is v at 0 momentum. And 0 momentum means long range interactions, right? Or 0 plus if you want, right? So this is small momentum in frequency space translates into large distances in real space. So if I'm Fourier transform this and take the 0 momentum contribution, I'm taking the long range contribution. So if the interactions are long range, like 1 over r square, this is actually a large number, and that's the point here is that this is going to be a contribution that is valid is very relevant for long range interaction. Okay, but now what I'm left with is these integrals in k prime and omega prime. There's this factor here, and there's the free propagator g omega here, g0, which is going to give me this delta function here. And here you have, this is actually this is the same index, right? I'm returning to the same point, so it should be diagonal, right? So let's call this sigma prime or something. So this is the same spin. All right, so this is the same point. All right, now how do I calculate this integral? The first thing I need to do is to figure out what is the expression for the free propagator, and the expression for the free propagator will be in the assignment, and it will have this form. There will be a delta function in spins here, and for the electron gas, it will have 0 temperature. So this is 0 temperature, okay? it'll have this form. It's going to be a theta function of the absolute value of the momentum minus kf, right? So kf is the Fermi momentum, divided by omega minus epsilon k. This is the free electron energy, something like that. And you have here a positive pole, a positive small imaginary part, and this will take to 0. And here I have the negative minus the imaginary part. So you can obtain these results in different ways. And notice that this is resembles very much the Lyman representation that we discussed. So it would be like particle and antiparticle processes. Okay. Now notice, and this is crucial for us, that the sign of this imaginary part is opposite in these two terms. Okay. So here, the poles here occur at omega equals minus eta. So these are poles below, slightly below the real axis, and here they occur at plus I eta. So this will be important when we do this integral here. All right. So okay, what we have to do now is just plug this, and this is actually, there's a 0 here, right? This is the free propagator. And we plug this in there, and let's evaluate the integral of the frequency first, and then we see what happens to the integral in k prime. Okay, so let's see. Let's plug this in there. So plugging this into this expression, we're left with the following integral in the frequency. Integral of, let's put it here, minus infinity to plus infinity d omega prime over 2 prime, and there is that factor e omega prime eta 1. This eta might be a little bit different than this other one, okay? But we're taking the limit of both to 0. So let's see what we can do here. All right. So as I mentioned, I have these expressions with poles. In this case, slightly below the real axis, and this slightly above the real axis. So one thing that we can do here to evaluate this integral is to evaluate it in the complex plane. So it would be something like this, right? So I have the omega here, or if you want omega prime, it's real part of a complex number z prime, and I have the imaginary part here of z prime, and I have, of course, these poles here. Let's call this A. The A poles are here, and the B poles are here. Okay, notice now this factor here. So when I go from this to an integral where I replace omega prime by this z prime, I would have something like this. I would have something like an integral in z prime, and I'll have to choose a contour that will allow me to reflect that this goes from minus infinity to infinity in the real axis. But essentially I would get something like this, Ez eta 1, all right? Then there's this theta q minus kf over, and now I'm going to put z prime plus I eta minus e, oh, this is, I put q, it should be k prime, sorry. This should be k prime, which is the other integral we're going to do. K prime, k prime, k prime, k prime. So is what we had before, right over there, right? K prime. Minus epsilon at k prime. And this has theta kf minus k prime, z prime minus I eta minus. Okay. Now notice this term here. When we do the integral here in the complex plane, we would like for the function evaluate at the edges of the contour, like the border that goes to infinity, to go to 0. So we would like, so for very large imaginary parts of z, this to be 0. So notice, however, that if we want to do that, e to the I times imaginary part. So yeah, let's do this the proper way. So if z prime is a real part plus an imaginary part, e to the I z prime eta 1 is e to the I a etas, which just oscillates, doesn't go anywhere, plus e to the minus b eta 1, all right? All right. So this means that we want b to be positive, right? If b is negative, then this term increases very much, even for eta small, and the integral will essentially explode. So we'd like to take a contour here that does that. So let's take this and then goes this way, right? Like this and like that, and encloses only these poles here. So meaning that the integral for this part will be 0, and I'll only enclose these poles over here, so b has to be larger than 0. B larger than 0, and this is b larger than 0, so that the integral here goes to 0, and we can perform this integral. Notice that then we can only do that because we added this term coming from that same time propagation. So this is crucial that you add this term here, right? So that you can evaluate this integral here and it doesn't explode in your face. All right, so if we do that, then we take this contour. It means that taking that contour, then the integral of this part is 0 because there's no poles for this part inside the contour. The poles are down here, and all I'm left is with this one. So, and then what I have, of course, I now evaluate the function at the poles, multiply by 2 pi, and I times 2 pi, and then the result that I get is simply this. So the result for the integral, it's just the sum. The poles, I get I times theta kf minus k prime. Oops, sorry. Which is these terms. Okay. So z minus eta. Actually, well, there's not many poles. There's just one, right? Yeah, thinking of Matsubara frequencies, but there's only one pole here. Yeah, there's this pole, which is z equals z prime equals plus I eta, and that's the only one. And yeah, so in the limit of everything going to 0 both, so this will decay anyway, right? So when I take the contour, so this is all that I'm left with is with this point, and the function here evaluated at pole is just theta kf minus k. All right, so that's the result for this integral, and now we can go back to our integral up there. Okay, so we're back to our expression. So we evaluated this integral here in omega and figure out this I times this kf minus absolute value of k prime and see what we're left with. So let's keep going. So this one is going to be then this propagator squared sigma prime k omega, and this is just the little legs, so it doesn't matter much for us. But this is the part that comes from the proper self-energy, which is v at 0 times this integral in d3 k prime 2 pi cube times the result for the integral in omega prime, which was I times theta of kf minus absolute value of k prime, right? And what does that mean here? What does theta kf minus absolute value of k prime means? It means that I'm integrating over a sphere of radius kf, right? Because this is 0 if absolute value of k prime is larger than kf, and 1 if kf is larger than the absolute value of k prime. So it means that I'm integrating in a sphere in k space with a radius equals to the Fermi wave vector. Okay. So what's the volume of this sphere is for well, we know what the volume of this is, right? If you go back to the class on the electron gas, the volume in K is, the total volume in K is 2 over cube the volume for 1, or this is the volume in real space times the number. So if you remember this is the volume of one state here, right? There was this little cube in K space where you have 1 over Lx, 1 over Ly, 1 over Lz, and the volume of this little cube is 2 pi cube divided by n over v. So this is essentially proportional to the density. Okay, you can go back to the class on times the density, and that is the density. The class on the electron gas, and figure that for yourself. So yeah, this is just I times the volume of the sphere. So the end result here is that I have the propagator square again, sigma prime, k omega. There's an I here, okay. There's an I coming from here. This square potential at 0 momentum times the density. And this is the density. So this is the Hartree contribution, directly proportional to the density. Okay. Now for the calculation of this diagram, the expression here, or at least the way to do the calculation, is very similar. Once we set up all the momentum, right, and we label them. Here I change a little bit the notation, since we always have to integrate over momentum and frequencies, internal momentum and frequencies related to the propagating lines. I essentially changed the variables here so that this propagating line has momentum k prime, frequency omega prime, so that the momentum of the interacting line is q k minus k cube k prime. The other point here that I'll take a little bit more care is about the internal indices of states. In this case, there will be spin, since we're talking about electron gas, right, where k is a good quantum number. But remember, for every vertex, for interaction, we have indices coming in and coming out of each vertex. So here, these two indices are the same, sigma 1. And so sigma prime comes in here, sigma 1 goes out, sigma 1 goes back in, and sigma goes out. So there is this so I have to sum over sigma 1 here. It's going to be a delta function anyway. Everything will be, this will have to be equal to that, and so on. But you have to sum over sigma 1. All right. Yeah, let's put the sum over sigma 1 here. Okay. So let's write down the series of propagators. So we have this propagator here from sigma prime to sigma 1. That's this one. K and omega, frequency omega and momentum k. There is now this propagator from sigma 1 to sigma 1. Omega prime, k prime, that's this one. Okay, IG0, the free propagator. This remember comes from a same time propagation. Essentially, it links the same two vertices that the interaction line connects. So this is clear same time propagation. So we have to add this term e to the I omega prime eta 1. All right, and then finally there's these other propagator. Frequency omega, momentum k from sigma 1 to sigma, which is this one. And we integrate over the internal variables, k prime, omega prime, and sum over sigma 1. Okay? All right. So that's the whole thing that we have to do. Remember that the momentum of the interaction is k minus k prime, and it's not 0. This is important. That's the important difference from this diagram to the previous one. All right, so let's do the integral in frequency that we did before. I mean, these two factor out. I still have to do the sum in sigma here. 1. But before we do that, let's figure out the overall sign of this term. So I have I times I gives me I squared minus 1. Then I have minus I here times I get a plus 1. So the overall sign is minus 1. And this is also different than the Hartree diagram where the overall sign was plus 1. Okay. Now, if we go back here and we do this integral, this is essentially the same that we did before. So the end result, if you do the complex integration here, you will be theta of kf minus absolute value of k prime. And there's a delta sigma 1 here, that when I sum over sigma 1, we'll get these two equal. All right? So at the end of the day, what do I have? I have this integral over k prime. V is k minus k prime. Okay? So that's a V, sorry. A V here. And this is k prime, not q prime, k prime. And that's it. There's no delta C, nothing here. But there's this minus I that comes from this. Okay, so if I now add 1 and 2, this should be equal to I times G of N1. So let's see what we have and how can we discuss the difference between these two. So putting everything together, we have, there was the contribution from the Hartree diagram right here. There's an I here, I cancel with the I here. There's a minus I here, I cancel this I with this, so we have the correct signs here, and there's this G sigma prime squared that comes from these propagators. Okay? All right. Now, this one, the Hartree, gives me a contribution that depends on the zero momentum component of the potential times the density, while this one gives me this integral, which is, if you look at it, it gives me a component in U k minus k prime that, of course, this k prime is limited to the Fermi sphere, but k is precisely this parameter. So this is a difference between k and k prime, and this difference can be small, right? And actually this is a v. But depending on k prime, see, k prime can be 0, right? Can be right down to the middle. So this can be as large, this contribution can be with a k as large as kf. So large k means short range, right? So if I would, depending on whether this interaction is actually long range or short range, this term might be more important or relatively to this one. So if we look at the plot, say, let's plot here V of Q, okay? And C as a function of, say, Q absolute value. All right. So this is the Fourier potential of the real space potential. So if our potential has very long range, I would expect this to be something like to decay fast, right? So this is long range. So it means that it will decay slowly in real time, in real space, but decay fast in momentum space, right? It's just a Fourier transform. Now, if this would be short range in space, say a very, an interaction that is collision-like, right? Very short range. Then by the same token, it means that spreads out in momentum. So this is short range. So, okay. Now, if these, so this is Q equals 0, right there, right? So this is 0. And yeah, this might be, yeah, they might not have the same, I mean, this, perhaps I didn't plot it correctly here. I have to take the real potential, but it could be something like that. Something like that. Or something like that, right? Doesn't have, they don't have to have the same value at 0. What I mean is that in the long range it's more concentrated near 0, right? It will depend on things like the actual form, the prefactor, and so on, screening and whatnot. So, but this is more concentrated. Means that for long range interactions, the Hartree terms will dominate, because this is stronger at small momentum. Now, for short range interactions, you can actually have a regime where the two are equivalent, or the exchange term it can be important, right? Yeah, to have a feeling for that, let's try to write this integral, or at least qualitatively here. Would have something like this. Would have, say, yeah, there will be the prefactors, there will be a 4 pi coming from the angular integral. There's this 8 pi cube here, but you would have something like that. 0 to kf, right? Something like k prime square dk prime. Then I would have something like that. vk minus vk prime. All right. Of course, it would depend on the form of the potential. But if this is spread out, like here, and let's say kf is around here somewhere, right? You're integrating this, and this will be your function of k at the end to compare with this. So if this is for a given k is about the order of v of 0, or right, same order magnitude, if you have a long range scattering, so that you might match what you have right there, then this term will be of the order of this one, and you might have these exchange interactions coming. But notice that this is a function of k. Right, so it will depend on also on which momentum you're talking about. Notice that this depends on the difference between this momentum and what you're integrating here. So with how the distribution of this in momentum space will be crucial. So whether it's short range or long range will make the difference, whether this exchange term or the direct term will be more effective. Now, the Coulomb interaction is long range typically, right? So why would you get a short range one? Well, there are physical processes that give rise to that, and we're going to discuss some of them in a class when we discuss the RPA. but that's essentially due to screening. And the interactions itself will renormalize the bare Coulomb potential and make it more short range, where then these terms will be important. So we're going to discuss that. This is a very important point with a strong physical meaning on the screening of the Coulomb interactions. And that's why at the end of the day, sometimes the screening can be so large that the interactions become so short range that this perturbation scheme actually works, and that's why even the non-interacting description works so well for metals, for instance. But we're going to discuss that in another class, but just to illustrate how we can at least evaluate these diagrams and get some insight on the physics of what's going on there. All right, see you next class.